Let's do the Lewis diagram for carbon monoxide. But before we start, it's worth mentioning that carbon monoxide is a colorless gas. The difference between it and carbon dioxide, that's a critical one, is that carbon dioxide, while toxic, really isn't that bad in terms of percentages. For example, you exhale 4% carbon dioxide, but exposure to carbon monoxide in terms of even 1/100% can be fatal. If you pull up carbon monoxide, one of the first sites that you'll get is the Center for Disease Control talking about carbon monoxide poisoning because it's a serious problem. Each year, hundreds of people in the U.S. die of carbon monoxide poisoning and thousands are hospitalized. That's because it's found when you end up having anything that you burn that's got carbon in it, from coal to methane to gasoline. If it's burned without proper ventilation, you not only get carbon dioxide, but toxic amounts of carbon monoxide. Anytime that you end up burning something, you really should have good ventilation because of the danger of this colorless, odorless gas. If it's present in fractions of percent, it can be lethal. That being said, let's do the carbon monoxide Lewis diagram. Of course, when we do Lewis diagrams, first thing we do is figure out the valence electrons. The electrons that are going to be around this molecule that we have to worry about, and the electrons that will provide the bonds in this molecule. Carbon being in the 1, 2, 3, 4th column here, if you ignore the transition metals, would end up having 4 valence electrons. 4 electrons in its outer energy level, the second principal energy level. Oxygen, 2 across, will end up having 6 valence electrons. And you've got to be able to count those valence electrons to be able to do a Lewis dot diagram or explain covalent bonding. Even though we've got electrons buried in the first energy level, they're not going to be involved in bonding. So we only have to deal with 10 valence electrons. Not that many for even just 2 atoms. First thing that we'll do is we'll have our molecule here, and we've got our carbon and an oxygen. With 2 atoms, it's sort of hard to figure out who's going to be the central atom, but it really doesn't matter, even though I would pick carbon because it's almost always a central atom and it has a lower electronegativity. Usually you pick the atom that is to the left on the periodic table with a lower electronegativity to be your central atom. The first thing we've got to do is bond these two, so I'm going to get a bond, which is a pair of shared electrons, and put it here between the carbon and the oxygen. So steps, we count the valence electrons, and then we bond the 2 atoms together. And of course, that bond is a pair of shared electrons, so that gets rid of 2 electrons, and now we have 8 valence electrons left behind. This is 2 electrons. That's what that line represents. I'll put that more in the center. We have 8 electrons then left over to deal with. Since we said that the carbon is the central atom, our next step is to give the surrounding atom, in this case oxygen, its octet of electrons, that low energy combination where electrons are attracted to this oxygen. We put them in as pairs. I'll pick up a pair of electrons, one of these 8, and put it on the oxygen. That's 2 electrons. We have to give it an octet, so I'm going to copy that and paste another 2 there. Then I'll pick up another set of electrons and put it there. So we have 6 valence electrons that we've used up. 2, 4, 6. With this bond, our oxygen now has that octet that most of our atoms would end up requiring. You could have done this for the carbon too. What we've done is we've used up 6 valence electrons and we have 2 valence electrons left behind. Those 2 valence electrons then go on to our central atom, or our other atom in this case. Here we go. I'll put that there. We've done our steps so far. We've counted our valence electrons. We've drawn our molecule. We've bonded them. This is what is holding them together. This carbon's attracted to this pair of electrons, and this oxygen's attracted to this pair. That is what keeps these 2 together. Their mutual attraction providing a lower potential energy. We've given our surrounding atom, arbitrarily picked as oxygen, and it has its octet. Then we check as our next step our central atom to see if it has an octet. In this case, 2, 4, no, doesn't have an octet. But we don't have any electrons left over to give it. We've used all 10 electrons up. If you count, there's the 10. So the only way to get carbon to have that stable octet, that lower potential energy octet, is to take this pair of electrons and bring them over. Now, the oxygen still technically has around it that pair of electrons. It's sharing them, but still it's there. And then we look and we see we have 2, 4, 6, not quite enough, so we'll take another pair of electrons and put them sharing here. Now our carbon has 2, 4, 6, 8 electrons. Rather than showing them here as separate dots, what I'll do is I'll just draw in a line and use that as the replacement for those pair of electrons. This is what's traditionally done. We've made a double bond. The first bond is referred to as a sigma, the double bond, the second bond's a pi, and then we'll do this too. That's because the nature of that sharing is different. The pi bonds are not shared directly between the two atoms, but are shared above and below. Let's do a double check. Carbon has 2, 4, 6, 8 electrons around it. 2, 4, 6, 8 for the oxygen. This is a bit unusual, though, having 3 bonds with an oxygen. If we look at this and say, this is strange, because usually we don't have a pair of electrons around the carbon, so let's check out the formal charge on this. If you were just asked to do a Lewis diagram, this is it. You're done. It would be a valid, correct answer. However, just sort of look at the formal charges of this. So I'm going to take and draw circles around each one of these atoms. That's a square. I should really be changing that to a circle. So I'll just go to my choice here and make that a circle and draw the circle around my oxygen to show the electrons that it sort of controls, and do the same thing around my carbon. Since I've done the carbon right now, let's do the count of electrons that are being controlled. 1, 2, 3, 4, 5, because the carbon is sharing this bond, which contains 2 electrons, so we say it's going to control 1, 2, 3. Now, carbon normally has 4 electrons, but in terms of its valence shell, 4 valence electrons, but 1, 2, 3, 4, 5, it's controlling 5, so we would end up saying that carbon formal charge -1. Now, this is a neutral molecule, which means that this oxygen by default should have a formal charge of +1, but let's just double check. 1, 2, 3, 4, 5. It has control of 5 electrons, but it's supposed to have 6, so it's missing an electron, so its formal charge will be a +1. Now, this isn't an ideal, it's sort of a stressed formal charge, because if we do have to have formal charges, we normally have the negative charge with the more electronegative substance, which is the oxygen. In this case, we've got that reversed. We don't have any other choices in drawing this molecule. I mean, this is how we've got to draw it. There's no other options. We can't change things without messing up our octets. While this isn't an ideal, in fact, actually it's sort of a strange formal charge, it's the best that we can do. But it's worth noting that this is an unusual structure. This sort of indicates a little bit of how and why carbon monoxide is so much more reactive and also dangerous than carbon dioxide. Oxygen and carbon combination will stick to hemoglobin far more than oxygen does. That's why it's toxic. But there's other ways of drawing this. There's another method that's referred to as the molecular orbital structures, where you take the orbitals of the atoms, like the carbon's a 2s and a 2p. Here we've got our 4 valence electrons, and you sort of toss them into our molecule, and you do the same thing for the oxygen, and end up tossing that in, and then you create specific orbitals for our new molecule. And that can provide a better explanation, but that's not AP. AP just asks a better way of showing things, but it's so complicated that it's much easier just to go with the Lewis diagrams. And that's it. Lewis diagram for carbon monoxide.